let's start. We can begin our seminar, and it's a pleasure for me to introduce our today's speaker. It's Karam Allali from University Hassan II of Casablanca, and the title of today's talk is Optimal Control of HPV Infection and Cervical Cancer Cells. Please, Karam, you can begin.
Hello, thank you everyone for attending my talk today. Before I start my talk, I would like to thank Professor Vital and Dr. Anastasia Mozokhina for the invitation for this talk today. Thank you all for attending the talk. My talk will be today about optimal control of HPV infection and cervical cancer. So the outline of my talk will be as follows. I will start by giving the mathematical model of the problem, and next I will try to give the well positiveness of the problem. To do that, give the dimensionless form of the problem. Next, in order to show that the problem has well positiveness results, I will show some results of bondedness and positivity results. Next, I will try to give the optimal control analysis of the problem. First, I will give the optimization formulation of the problem. Next, I will give the results concerning the existence of the optimal control. Then I will give the system, the optimality system. The numerical simulation will be given, and after that, I will give some numerical simulation. The talk will be about two kinds of incidence function. The first one is saturated function, and the other one concern the problem with Bident de Angelis problem. For the first, I will give the equilibria and the local stability of the problem with the saturated rate, and the numerical simulation to the problem with the saturated rate. And after that, I will give some conclusion and references. Okay. Now I will talk about the HPV infection and cervical cancer. Some literature about this kind of problem. The first, maybe the first work about the causality, talking about the causality between HPV and cervical cancer was first established in Schwarz et al. In Nature, and after they work heavily, and the first in 1985 and the second one in 1987 by Devilliers et al. So the causality between HPV infection and cervical cancer, this causality results, the first causality results, was rewarded by Nobel Prize in Physiology in 1985. The results is mainly about that these viruses when it attack the epithelium in cervix. It cause a cancer in cervix, and it was cervical cancer. So this causality, as I said before, has been rewarded as a Nobel Prize in Physiology. This is very important reasons about some cancers that can be originally from viruses. The virus is HPV, abbreviation of human papilloma virus. After that, many works have been fulfilled about the dynamics and the mathematical modeling about and HPV and cervical cancer. There is many. Some of those works I cite, for example, the mathematical modeling by 5 main compartments is studied in ASIA. It all in 2016. The 5 compartments are HPV, human papillomavirus, also the susceptible cells, and the susceptible cells becomes infected by the virus as human papillomavirus, and after that we have precancerous cells, and after that the cell become cancerous cells.
Excuse me, Karam.
Yes.
We don't see. I don't know what slide do you show, because we still have slide number 3, and you describe the model and different cells.
Okay. Just I want to say only this the five main components.
Yeah. Okay. So it's correct. Yes, you show slide number 3, right?
Yes.
Okay, because I thought that maybe you moved forward. Yeah. Okay.
It's only.
Okay. Sorry.
I'm thinking about what is done in the point 2 and what is done in mathematical model.
Yeah. Okay. Thanks. Sorry.
And this mathematical model, they take only bilinear incidence infection rate. The optimal control of the model by these 5 main compartments is have been made in Chakraborty et al. 2019. In 2021, the optimal control with saturated infection rates have been done in 2021, and by changing the saturated infection rate by Bidet dangerous functional response, it have been done in Biomat conference. It's expected to appear as a chapter book. The 5 compartments model. I will try to make it to zoom. Okay. So the 5 compartment models is, as you say in your computer. So we have five compartments. The susceptible cells, the infected cells. There is some there is some precancerous cells P, and the cancerous cells. It's denoted by compartment C. So the birth rates. There is some arrows between different compartments of the disease. So the arrow coming into the compartments is like it's growing. It's participating to grow the compartments. However, the arrow going from to outside. Maybe death or conversion to or transition to other compartments. For example, lambda is the birth rate. The birth rate of there is some birth rate. The birth rate of susceptible cells is lambda. The birth rate of infected so not the infection rate, for example, the infection so the force of infection is here. We take Bidden de Angelis rate, and there is some death rates, D1, death rate of infected cells, death rate of precancerous cells, D2, and death rate of cancerous cells, D3. Here the death rate of viruses is D4. So the infection rates here we have taken the Bidden and de Angelis rate, but in the work, the last part of this talk, I will talk about saturated rates. So we can have saturated rate when rho it's equal to 0. Here we have taken two controls. The main in the optimal control problem, we have taken two controls, V1 and V2. V1 is the interest of V1 is to minimize the infection force between that cause virus and susceptible. It means that we minimize the infection rate. For example, if you see here when V1 is equal to 1, it means that there is no infection. And when V1 is 0, we have the maximal value of the infection. Here another control, V2. V2 is to we act on the infected cells in order that we will have a minimum value of the viruses. So there is here two therapies or two treatments. The first treatment, V1, acts on the infection rates of between viruses and susceptible. However, V2 treatment acts on to minimize the amount of infected cells. Why these things is possible? Because the infected cells produce many variants. So if we minimize the infected cells, we can minimize the free variants. Here the delta is the rate that infected cells become precancerous cells, and this value eta 1 p squared k plus p squared over k plus p squared is the rate that precancerous cells become cancerous one. Mathematical model is given as follows. So here the first equation concerns the susceptible cells, while the second equation is the affected cells. And with so we take here logistic growth of susceptible cells. Here we have the force of infection is F depending on S and V. And and you have 5 compartments. So the first equation describes the evolution of susceptible cells. The second equation describes the evolution of infected cells. The third equation describes the evolution of immune papilloma virus. P describes the evolution of precancerous cells, and the last equation describes the evolution of cancerous cells. Here in the first work that I present in the slide before, the first incidence function was the subject of the previous works, and this generation was the subject of another work in Biomat 2023. And we have if rho is equal to 0, we can return to the saturated infection rate. Dimensionless, in order to have the dimensionless model, some parameters are introduced. For example, A, it's equal to D1 minus B1. B is equal to D2 minus B2. K is equal to D3 minus B3. And to have dimensional form, we have introduced new variables to the problems. S1 is equal to S divided by N. I1 is equal to I divided by N. P1 is equal to P divided by K. C1, C divided by K. So if we, for example, and N is total the total cells, total number of cells. So if you see S1, there is no dimension because cells divide by cells, and we have no dimension for the dimension of S is cells. However, cells per microliter or cells per millimeter cube. So if we divide by the unit, we can have no units for S1, etc. So the dimension of cells, it's number of cells. So here we have a number of cells per microliter, or number of cells per millimeter cube.
Yes. Excuse me, Karam, I think that we have a question from the audience. Anastasia, do you have a question?
No, excuse me. I'm sorry.
Yes, okay. No questions, so continue, please. We keep questions for the end of your presentation, so continue. Come.
Okay. So we have here the new model without dimension. So for more simplicity, we introduce some other parameters, and we have we omit the indexes in order to facilitate the manner how we write the new model. So the new model is given by this new form with some initial conditions for S, I, V, P, and C that we will assume to be non-negative. So we assume that the initial conditions are non-negative. So the problem dealing with the population dynamics. Here the population are cells. So the solution of the problem exists, remain non-negative and bounded. Some idea of the proof is we make here S in S equal to 0 to 0. Similar by I is equal to 0. And we have from this we have that that all variables of the problems are positive. For the boundedness results, we can add the two first variables, and by derivative can have that derivative of the summation of susceptible and affected is lower or equal of lambda t 1 minus t, which gives us the boundedness of the variables. We can replace this in the other equation, and we have the boundedness of all variables. So we can say that the problem is well posed. The optimization problem, in order to have the form of the optimization problem, the idea is to change the control, the constant control into we vary the two controls, V1 and V2. So V1 will be depending on T, and V2 will depend on T. And we are looking for the best optimal control that allowing us to minimize the infection. So if here, as you say, we are acting on the HPV infection, and we will see their consequences on the replication of precancerous and cancerous cells. The question is, if we act on virus, shall we get good results on cancerous and precancerous cells? This is the question. Now, we're not here in this model. We are not acting on treatment on cancerous or precancerous cells, but only we are acting on theoretically, of course, mathematically, we're acting on the first stage of infection. For example, we are acting on the infection by virus. if we act on virus, minimizing the infection between susceptible and the infection between the virus and susceptible, we are acting on minimizing the production of VHPV viruses. If we'll have minimization, will the precancerous cells and cancers will be minimized or not? So in order to study the optimal control problem, so the optimization problem consists in maximizing the following objective functional. So G depends on V1, V2. It's the integrand between 0 and TF of ST minus A1 divided by 2 V1 squared plus I2 divided by 2 V2 squared. So this objective functional, we want to be maximized. So if we maximize this, means that we maximize the susceptible, and to reduce, we want to reduce the costs E1, A1, and A2 that are relatives to the two controls V1 and V2. TF, of course, TF is the final time of treatment between day 0 and TF. It's the final time of treatment. So here we have, we'll seek an optimal pair, control pair, V1 star, V2 star, such that G V1 star, V2 star, it's equal to maximum of G V1, V2, V1, V2, it belongs to one control set, U. Here, some classical theorem in optimal control existence. There exists an optimal control V1 star, V2 star belongs to U, to set U, such that G V1 star, V2 star is maximum of G V1, V2, V1, V2 belongs to U. The proof of this theorem is classical, and it's enough to prove the 5 points. The first point, the problem states variable R and control sets are as no T. The control set is closed convex. The states system right hand side is bounded above by a linear function which depends on states and control variables. The objective functional integral is concave, and the vector function is bounded above. So in order to have the optimality system, let's give the Hamiltonian function h given as follows. H, it's equal to A1 divided by 2 V1 squared plus I2 divided by 2 V2 squared minus S plus summation of I, Gi. So Gi, first remark, we this value between A1 V1 squared E2 V squared divided by 2 minus S, we can see this amount in the objective functional that I showed before, plus this summation. Summation is given by so G1, G2, G3, G4, G5 is given in the are given in the right hand side of the problem. So the G1 described the evolution of susceptible, G2 described the evolution of infected, G3 describes the evolution of infected cells, G4 precancerous cells, and G5 for the cancerous cells. From Pontryagin maximum principle, we have for any optimal controls, V1 star, V2 star, and solution S star, A star, V star, P star, and C star. The states system for before that we have shown before, there exists adjoint variables phi1, phi2, phi3, phi1, phi2, phi3, phi4, and phi5, satisfying the following equations. Phi1 derivative of phi1 verify the first equation. The phi2 prime derivative of phi2 verify the second equation. Derivative of phi3 verify the third equation. The derivative of phi4 verify the fourth equation. The last equation is satisfied by the derivative of phi5, the derivative of phi5. And the transversality condition phi I and at the final time treatment time is 0. In addition, the optimal control will be given by V1 star is under the formula of minimax, and V2 star is given by min-max formula. What we can understand from these two formula, that's V1 star, V2 star doesn't exceed 1 and cannot be under 0. This is why you can make min max. It means that at any conditions we cannot have V1 star more than 1, less than 0. The algorithm to find the optimal control is given by the following. The first, so we have the first initial conditions. We have V1 and V2. We start that there is no control, and here we have phi1 M0 is given in the following previous theorem. Main loops is given by the following algorithm. This algorithm is given by we have Q1, Q2, Q3. So we can make Euler, but it's more adequate to make Ronge-Coulthard 4. The Ronge-Coulthard 4 is more you have more stability. But if we want to solve this by Euler, we need to. It's less stable. That's Ronge-Coulthard. Ronge-Coulthard more stable. And what we have to do in this it's called this scheme is called forward backward scheme. Why we call it forward backward scheme? Because we solve the variables in forward manner. However, the adjoint variable phi I is solved in backward manner because we have the initial condition in the CIM, the last point, and we have the initial condition. However, we have the initial condition for the variables from 0. So this method, it's called forward backward difference scheme. And range quota also, and we have this formula, minimax formula, in order to have the two optimal controls. In the numerical simulations, we have satisfied numerical simulations. So we have from the beginning they are the two cores coincide, and after some first days of treatment, we can observe that without control we get the number of susceptible to green plot are maximized. However, without control, we have less amount of susceptibles. Opposite remarks are observed in the figure on your right hand side, which means that with control we have less amount of the infected cells, green plots, and we have more amount of the infected cells, blue plots, in your right hand side. These three figures show the dynamics of HPV, human papilloma virus, precancerous cells of in the cervix, and cancerous cells. So with control, the green curves are in these three curves are less. The amounts of this of the amounts of HPV, precancerous cells, and cancerous cells with control are less than without control, which means that this is very important to see that if we act only on the infection, we can have good results in precancerous in P compartment and C compartment. In mathematical model, we didn't act on precancerous cells directly. We have acted implicitly, not explicitly, and we have get good results on precancerous and cancerous cells. Now we'll see the dynamics of the two controls. So the first controls, the two controls, the left-hand side and the right-hand side, starts from 0, and it's recommended to take drugs in increasing manner, and until the first day, and after that, after some first days, the first control should be taken in the maximum way. However, in this from the day 15 to nearly day 80, the first control should be taken under maximum way. However, there is no need to take the second treatment. However, we see that the first control is decreasing until it's reached some stabilize in some value, maybe 0.9. And however, the V2 is increasing and be stabilized in some constant value. So the first problem with saturated problem, the problem with the bidon rate, we didn't be interested in the equilibria and in the stability. However, in the problem with the saturated rate, we have given some results concerning the basic reproduction number and its influence on the equilibria stability. So the basic reproduction number is given by this value. What is new here in the basic reproduction number with the therapies is that R0 is depending on 1 minus U1 multiplied 1 minus U2. The two controls here, fixed controls, which signify that each drug operates independently. So and this some plots show that if we plot this, we can see that the controls influence the value of R0. The steady states, we have some steady states, E0, which represents the total absence of cells and virus. This is it's not important to study this because there is no biological interest to this E0. So and also there is E1, which represents the absence of the infection and total presence of healthy cells. E1, the free equilibrium, and there is two other steady states, E2 and E3. The E2 is given by this little bit complicated some formula, and this is by calculating E3, we have that EI3 is negative. So E3 has negative components, so it does not take into consideration. The local stability of the disease-free equilibrium E1 is locally asymptotically stable when R0 is less than 1. Donc, Jacobian matrix. So the Jacobian matrix, the idea of this proof is to take the Jacobian matrix. The Jacobian form of the matrix is at any point is given by G1, 0, G2, G2, G3, and G1, G2, G3 is given by this formula. If we calculate the eigenvalue, we can see that G3 the eigenvalue is negative, and the G1 eigenvalue is negative when R0 is less than 1. The endemic equilibrium E2 is locally asymptotic stable. We compute the eigenvalues and the characteristic polynomial And we have this conditions. These conditions ensure us the root Hurwitz condition of local stability that the eigenvalue has negative rules. Numerical simulation is close to the results with redundant homogeneous results. So here also by administration good therapy, an optimal control, we have that here the susceptibility table is maximized, going to 1. So here it's very important to this the results. That's by taking good therapy, we change transit from endemic equilibrium to the free equilibrium. So here we as you see, the value of the susceptible is 1. However, the infected cells here is 0 with control. So this control, we can change the nature of the equilibrium. It means that we change the attractor. It means that we can take it like bifurcation parameters, because we have changed the nature of this this attractor. Here also virus, HPV virus, precancerous cells and cancerous cells. You can see clearly that we are transiting from endemic equilibrium to the free endemic equilibrium, which means that we can act only on HPV infection, and in order to see good results on the infection. So this is the behavior of the two controls. Here we can see that the controls are maximum, should be taken in increased magnitude during first day, first months, and after that it be decreasing until reaching some stabilized value of treatment. It's different from the first study, because the first study, the first control attains maximum value 1, and however the second one attains 0 value. This is very different from the first numerical simulation. As concluding remarks, we have studied the HPV infection with Bettenton Angeles functional response, as well as the saturated rate functional response. Two controls are incorporated into the suggest model. The well-posedness of the problem is established. The optimality system was given and solved numerically. The numerical tests have shown the essential role of administration good therapy in reducing HPV infection. It is so important to administer good antiviral therapy in order to reduce cervical cancer cells. Some references about HPV and cervical cancer, starting from the pioneer work of 1985, Schwarz et al., and other works in mathematics dealing with HPV and cervical cancer. Thank you for your attention.
Yes, thank you very much, Karam, for this presentation. It is an interesting problem. So we have some time for questions and discussion. So please, if there are questions in the audience, we can ask them now. And waiting for the questions from our listeners. Well, I have several of them. And the first one about the biology, because in this, I think in this seminar, we did not discuss how viral infection can initiate cancer. So do you have some biological insight? What happens with infected cells? Why? What are the biological mechanisms? How they can become precancer cells and later cancer cells? Because the most important characterization of cancer cells is the unlimited and uncontrolled division with self-renewal. So somehow viral infection modifies this genetic program and they begin to divide. So what is happening there? Do you have some biological insights about that?
Yes, when I read some works, I was very surprised to see that this kind of concept is initiated by virus. I don't know if other concepts are initiated by viruses or not, but for this kind of disease, it's very astonishing to see that this kind of virus HPV initiates the cancer proliferation, cancer cells proliferation.
Yeah, it's a really interesting and important question. I think that we need to read about these biological mechanisms which lead to this uncontrolled cell proliferation in infected cells under the influence of virus. So I have also another question about the model now. If you can return, please, to slide number 4, I believe, or maybe the next one where you show the equations or the scheme of these interactions between cells. Well, maybe this one. Yeah, it's okay. It's okay. So we see here that precancerous cells become cancerous with the rate. So there is this arrow, and below the arrow, there is this rate of transition. And this rate of transition is proportional to p squared, to the second power of cell concentration. Why it is second power? Is it because the cells interact with each other? Why not just first power of p here?
Really, I ask the same question when I work the first time in this paper. Yes, when I read literature about many works in mathematics, they have used the power 2. I'm also thinking about this part. I'm telling you the truth. This is I have read this in the works, and maybe I missed something, but the authors. I think about the papers that I read. Maybe there is some explanation in other papers, but still I'm looking for the answer of this question. Why p squared?
Yeah, it's also important to understand. Well, I can maybe make a hypothesis that these precancerous cells somehow interact with each other. For example, if the cells produce some cytokines and the cytokines act back on the cells, in this case, kind of this positive feedback or cell interaction, then we will have the second power of p. So it's an interesting question because, and also from the modeling point of view, because it can change, well, behavior of solutions of this model, the existence and stability of stationary points. So we can try to think about this question.
Professor Volpert, I have seen some incidence function 1 or k plus the variables power alpha.
Yeah. Okay.
Some literature about this, but p square on the top of the fraction. This is my yes. But below there is many incidence functions. Take 1 plus x, for example, power alpha. But the question is why p square on the top of the fraction?
Okay, let's then continue with the results of this optimal control problem. If you show, please, slide number 19. Yes. Maybe. Yeah. Okay. Yes. Exactly this one. Yes. Figure 2. Yeah. Very good. So, for example, if we consider the left figure is dynamics of susceptible cells. So we see here that in both cases, with control and without control, the concentration of the cells grows in time, of susceptible cells. Well, we can say of healthy cells. So looks like in the beginning, their concentration is very low, and then it grows even in the case, there are this viral infection, so cells become infected, but still the concentration of uninfected cells grows in time. Is it because the initial condition is chosen sufficiently small, or there is some other reason?
Maybe I should take other initial conditions in order to see what happened. But well, maybe I should change the initial conditions. Maybe.
Well, I suppose that different initial conditions can be considered, but maybe one possible choice of initial condition to take it as in the stationary solution. For example, it depends from what time we begin. If we begin to study our problem at the moment when virus is introduced. So if time 0 is the moment when virus is introduced in the tissue, then we can take as initial condition the concentration of susceptible cell equal to its stationary steady concentration without virus. It's one possibility, but there are of course other possibilities. So, but it is one of the equations or one of the parameters which can be maybe studied in the model. Right, and what I also noticed here in this figure and in the next figure that I think maybe it is more clear in the next figure. If you can show, please, in the next slide. Yes, here no, well, maybe I'm wrong. I don't know, because the concentration of virus, does it converge to 0 or it remains positive? Because it's not very clear in the previous figure for infected cells. I had an impression that their concentration remains positive, and here for virus it's not very clear. Is it still positive or it converges to 0?
Yes, you are right, because all these questions I have checked in the work with the saturated infection rates. because in the work with infection saturated rate, the virus go to 0, and
yes, I noticed in the end it was slide 27. Yes, no, 26.
Yes.
26.
Yes, you are right. In this work, I haven't checked this remark. Yes, I haven't checked this remark
because later for another functional response you explain that that control allows us to move from endemic equilibrium to disease-free equilibrium, and virus is completely eliminated. But here, maybe it is the same or maybe not. But
still, yes,
yeah. Okay.
Yes.
Okay. And also, probably the last question I'd like to ask is about it's slide 27, figure 7, where we show this optimal control functions for control functions for this functional response, Beddington, De Angelis. Yes. So these curves start from 0, then they grow and they reach their maximum, then they decrease. But why? So this corresponds to the treatment. So why we start treatment from 0 and then gradually decrease? Why we don't give from the very beginning high value of treatment? Isn't it more efficient to start not from 0 but from high values?
Yes.
At least, yes, please.
Yes, I didn't test this, but in our works with control, we have started by 0, but this is a good question. What happened if the control we didn't start by 0, by another value? Yes.
Yeah, this is. I remember in particular when we worked with oncologists, not on this type of cancer, but on leukemia. They explained that from the very first day of treatment, they give the maximal tolerated dose, because the purpose is to eliminate cancer cells as soon as possible. So they begin with the maximal possible value of, well, if we talk about chemotherapy, here it is different. So probably different protocols maybe are possible, and it is also interesting to analyze how we can achieve the best result, because it's not only the question of complete elimination of cancer cells, but also maybe how much time we need to eliminate them. So this is also, of course, important. Okay, I think I have all my questions. If yes, if we don't have other questions from the audience, I don't see. Yes, yes, we have another questions from Yana Lansova. Please, Yana, you can ask your question. And then also another question. Yes. So we have some more questions. Yana, please, you can ask your question.
There were 2 treatment methods included in your model. The first reflects the effectiveness of drug treatment in blocking new infections, and the second method in suppressing a new virus. So I would like to clarify if we are talking about any specific drugs, or are they some kind of abstract ones?
Yes, thank you for your question. Yes, about we have worked on optimal control of some disease like HIV and HBV, and we have explained for HBV like some drugs like interferon and And for us, I think for HCV, ribavirin, there is some drugs well known for some disease like HCV, ribavirin, and interferon, some interferon, if I remember well. But in cervical cancer, I don't. I have checked, but I didn't see some well-known therapies for this kind of how we take this to stop this new infection, or to block new infection, or to inhibit production of viruses. I don't know some well-known therapies in this disease, but in other diseases we have given some examples of V1 and V2.
Okay, yes, this is indeed it's an interesting question, because we know we studied in some other works the influence of interferon on viral infections. So maybe it can be also used as antiviral treatment for this disease. We have also another question from Kambolat. Kambolat, please, you can ask your question.
Hello, good evening. I would like to ask if there is any exact mathematical method which can show if a woman has already HPV virus that may grow into the cervical cancer, and also if this method can, the result of this method will depend on some variables which will show us that some components are out of normal indicators in our organism, which will or eventually warn us about that there's something wrong with our organism.
Well, this is a difficult question. Karam, can you say something about that? So I think that this is a little bit beyond the mathematical model. It's more a biological biomedical question. Are there some biomedical indicators which show the development of this cancer? Do you know, Karam, something about that?
No, no, I don't know. If I understand well, it's some biological aspect to add in on the model, I think.
Well, maybe. Well, I don't know. Maybe the first question to understand are the biological markers which can be used to determine this cancer, and then maybe at the later stage to include it somehow in the model.
I didn't study this in this the present study.
Yes. Right. So we have one more question from Vsevolod Kozlov. Vsevolod, you can ask your question.
Good evening. I wanted to ask about why do we reduce the dose of treatment on day 10? Does it depend on the success of the treatment or on other reasons?
Could you repeat, please?
I wanted to ask if why do we reduce the dose of treatment on day 10 up to 20? Does it depend on the success of the treatment or on other reasons?
To reduce the cost.
Yes.
To reduce the cost, it depends to the success of treatment. Yes, I didn't really. There's two costs, A1 and A2, and really this is a good question to see what's the dynamics of or what is the impact of the two treatments on the success of the therapy, or changing the equilibrium from endemic to free equilibrium, to see the impact. Yes, I didn't see this, I didn't check this, but Yes, this is yes. I maybe in some other works to study the impact of the two costs on and see the success with which it depends the success of the treatment, the optimum control on the costs. I didn't, but this is a good question. Thank you very much.
Yes.
Okay.
So the objective of this optimal control, as you say, is to provide the transition from the endemic equilibrium to the disease-free equilibrium. So this is why we need to give some sufficiently high dose of treatment, but at the same time, as you explain, we need to minimize the cost.
Yes.
The cost of this treatment. This is why, after reaching the most important objective, to go to the disease-free equilibrium, we need also to control the cost of the treatment. Cost, in the sense, it's something, well, the terminology used in this optimal control of biomedical problems. By cost, we understand not necessarily financial cost, but rather often it is understood as a side effect of treatment. For example, if we apply chemotherapy, we know that chemotherapy is cytotoxic. This means that chemotherapy kills normal cells, so people usually suffer from the side effects. So we need to minimize cost of treatment in the sense of minimizing the total amount of drug, for example. So the objective of treatment is, first of all, to reach this disease-free equilibrium. This means to eliminate the disease, but at the same time to minimize the cost, in particular the quantity of this treatment, and this is why the drug concentration, the quantity of treatment decreases after some time. But by the way, also what we can also see from this figure 7, that it does not converge to zero. This treatment which is suggested here in figure 7, it remains at some positive level. Does it mean that we need to give constantly some treatment, or that we can, once we go to this disease-free equilibrium, that after some time we can stop treatment? So this disease-free equilibrium, is it stable without treatment or unstable? Karam.
Yes.
Do you know that?
I understand. So according to the curve, maybe so the treatment should be taken very long time. But it's
yes,
very questionable. This very questionable this curve. However, I return back to the question about A1 and A2. So this curves, we have taken some fixed A1 and A2. It gives some results, and if we change A1 and A2, we have another result. And the question is, what is the best A1, A2 to have good treatments? Yes.
Yes, that's right. But well, there's also another possible understanding of that A1 and A2, they are given, that it's not like parameters which can vary to optimize treatment, but it is something which is given by the treatment itself. So that we cannot, that it is determined by the treatment, and we cannot really act on that. But anyway, all these questions are very interesting and very stimulating, as we see with this discussion, that there are really many interesting questions to think about, both from the biological point of view and modeling point of view. So thank you very much again, Karam, for this inspiring presentation. So since we don't have questions anymore, we finish our seminar. Thanks again, and thanks also to all our participants. Have a good day. Goodbye.
Thank you. Bye.
Thank you very much. Goodbye.
Bye.
Thank you. Goodbye.